This video is part 2 of a 3-part video series on performing magnetic resonance wireless charging measurements based on Air-Fuel Alliance standards. This particular video is focused on the power save state, making various timing measurements on short beacons, long beacons, as well as current and frequency measurements. The first step is to connect your current probe to the DUT. In this case, it would be connected to the transmitter coil or PTO coil. So let's go ahead and get started making measurements. I've got my current probe connected across the transmitter coil, and I have my arbitrary waveform generator simulating beacon current. The first thing is to optimize the vertical scaling. What most people do, and I think it's a good idea, is we'll go into the scope's roll mode, which is an untriggered mode. I'm going to slow it down a little bit. You can see the beacons going across. Now I'm just going to keep tweaking the vertical sensitivity until I can get approximately full scale across screen. There we can see a long beacon and many short beacons. And what a lot of people do is they make their measurements using this mode. When they see what they're looking for, they'll just simply press stop on the scope. And if they want to say perhaps measure what is the width of a short beacon, which is called T-cycle, zoom in, use the scope's cursors and make those measurements. Slide over here to a long beacon, which is actually a short beacon concatenated with a long beacon. Make measurements on that, again with cursors. The problem with this measurement technique is it's not very precise, it's prone to errors, and it can't be automated. The best way to make these measurements is once we have the vertical scaling set up, is then go into a actual triggered mode, trigger on specific beacons, and do these measurements automatically. So let's do that now. I'll go ahead and press run again. I'm going to go out of the scope's roll mode, select a normal trigger mode. Now I'm going to set up a trigger condition such that it will trigger on any beacon, long beacon, or a long beacon concatenated to a short beacon, or a short beacon. So let's go into the trigger menu. Now I'm going to select pulse width trigger, channel 1, which is my current waveform, a low condition for greater than 100 milliseconds. And I need to move my trigger level up a bit. There we go. So there we can see it triggering on any beacon, short beacon or short beacon concatenated to a long beacon. The first measurements I'm going to make are on short beacons only. So I need to isolate it so the long beacons aren't popping in there like you see right here. We have a special trigger feature called zone trigger. I can set up a zone, draw it in the area where the long beacons might be occurring, say must not intersect, and draw a second one over here on this second short beacon, zone 2 must not intersect. At this point we shouldn't see any more flashes of the long beacons popping in there, and so we have our short beacons isolated. The first measurement I'm going to perform is called T-cycle, the time between short beacons. What I should select first is go into a peak detect mode, and then I'm going to turn on a math function called max hold. So I'll select the max hold math function, and what that will do is it will plot a waveform that basically tracks the envelope of the peak values of the current. This is the waveform we can perform the automatic measurements on. So I'll select measurements. The default measurements frequency and volts peak to peak pop up. You can just ignore those. And now I'm going to select my source as math 1, and what I want to measure is the period. And this measures the time between short beacons. In this case it measures 250 milliseconds. The spec is 250 plus or minus 5 milliseconds. The next thing I want to measure is the width of a short beacon, which is called T short beacon. I could measure it immediately, but I could get more accuracy and more resolution if I zoom in on that short beacon, then select the plus width measurement on the Math 1 waveform. And there is the width of my short beacon. It's measuring 10.01 milliseconds. The spec is anywhere between 10 and 30 milliseconds. The next parameter I want to know is the settling time. The settling time is the time when current changes from one power level to another power level to 90% of the steady state level. For that, I'll perform a rise time measurement, but I don't want it from 10%. I want it actually from 0%. But I can change that by going into the settings menu, thresholds. I'm going to modify the measurement thresholds for Math 1 and change the lower level to 0%. Now I have the settling time from 0 to 90%. The spec during the power transfer state is less than 250 milliseconds. For a short beacon, the spec is it must reach steady state, or at least 90%, within 10 milliseconds. So we're within specification. The last timing measurement I'll make on a short beacon is the slew rate. Now I want to know what the slew rate is of the change in the current, not the instantaneous current. But this purple waveform is tracking the peak values. The slew rate specification is based on RMS. I can scale this waveform to represent RMS by turning on a second math function. We'll call it Math 2. And our scaling function is called AX plus B. My source is Math 1, and I can enter a scalar of 0.707. That will convert peak values to RMS values, and now I'll simply set the scaling factor, amps per division, to be the same as my current. There you can see a waveform that represents the RMS value. Now to get the slew rate, I'm going to perform a rise time measurement on this waveform and then modify the thresholds. Let's select a rise time measurement, but I need to change the source to Math 2 and a rise time measurement. So there's 2.08 milliseconds. We really don't care about that. This is from 10 to 90. Let's tighten that up to maybe 45 to 55, where the maximum slew rate is. I'll go into the settings menu, select thresholds, modify Math 2, and I'm going to change the lower to 45% and the upper to 55%. There's a rise time on a very narrow portion. Again, I really don't care about that rise time. What I care about is the delta I over delta T, which I can get by turning on the cursor's measurement, and it reads it out right here, 245.309 amps per second. The specification is typically milliamps RMS per second, which is the same thing since we've already scaled it to RMS. The typical specifications during a power transfer state, depending upon the resonator, is anywhere between 100 and about 180 milliamps RMS per millisecond. But for short beacons, those specifications don't apply since it has to reach the steady state value very quickly. So that's our slew rate on a short beacon. Two other measurements we're going to perform on the short beacon. They're not timing measurements, but the current measurement. What is the current during the steady state value? I'm going to slide my short beacon over. I've got about 7.3 milliseconds delay. It's steady state at center screen. Let's go to the summary, and you can see what the sample rate is. At this time-based setting, the scope is only sampling at 9.77 megahertz. So we're way undersampled. We need to zoom in on this waveform at this setting so that we can sample at 5 gigasamples per second and make accurate measurements. I'm going to zoom in to 2 microseconds per division. I'm going to turn my waveform math off since I don't need that anymore. Turn my measurements back on, and let's clear all these measurements and start over. What I care about is frequency and current. So there's our frequency measurement. Not enough digits. I'll fix that in just a minute. Peak to peak we don't care about. Let's clear it. Now let's turn on an AC RMS in-cycle measurement to get our current. So we're measuring about 585 milliamps. We have something less than 100 microamps of resolution, and with the statistics on you can see very stable measurements. Now back to the frequency measurement. If you saw video 1, I showed how to use the built-in 5-digit counter to more accurately measure frequency. We can't use that on beacons. That frequency measurement requires a continuous wave, not beacon. This frequency measurement, if I put the tracking cursors on, you'll see that it's actually measuring a single period and then taking the reciprocal. To measure across the full screen, I can turn on another math function, and I'll select Math 3 this time, and select Measurement Trend of Channel 1 based on frequency. And now I'm going to rescale this waveform. The purple waveform you see going across screen is it's plotting frequency on the vertical axis versus time on the horizontal axis. So these are frequency measurements of every cycle, and we have, I believe at this setting, about 135 cycles across screen. What I want to know is what is the average of this particular math waveform. For that, I can select the average full screen, and now we have a lot more resolution and a very accurate measurement of current. Next, we're going to perform some measurements on long beacons. First, I'm going to clear things up, turn my measurements off, turn my waveform math off, and now let's zoom back down. And there you can see a short beacon followed by the zone trigger that's saying do not intersect this zone. Now what I can do is I can change this to an intersect zone, say must intersect, and now the next time a long beacon occurs on a trigger event, then it will capture a short beacon concatenated to a long beacon. I'm going to rescale it a little bit, bring it down a little bit. It was getting a little too close to the top of the screen. And now we can go through many of the same measurements we made before. We'll go through them a little more quickly this time, and I'll probably skip a few. So if I want to measure the width of this concatenated short and long beacon, I could turn on my max hold waveform, which was already set up. There you can see the peak values, and then simply select a plus width measurement on the max 1 waveform. This is measuring 114.3 milliseconds, but remember this is short beacon plus long beacon, and we were measuring I think about 10 milliseconds on the short beacon measurement. So you subtract the 10 milliseconds, so we're measuring about 104.3 milliseconds. The spec is 105 milliseconds, plus or minus 5. The next measurement we'll perform is the settling time measurement. This is a little more difficult. We want to measure the settling time when it goes from a short beacon to a long beacon. Let's go ahead and turn measurement statistics off. I'm going to rescale again a little bit more, clear it, clear display, start over. I think I want to change my scaling on my math waveform to match my current to 260 milliamps. There we go. First thing I'll do is turn on my zoom time base and window in on just that step. And that will window my measurements or gate my measurements as well. Now the next acquisition we should see, there we should see it. If I zoom in on the purple waveform here, I'll do it and then I'll put it back. You'll see that it's pretty choppy. We don't have a lot of resolution. So let's put it back where it was, lay it back on top of that waveform. And let's go ahead and set the scaling the same as it was. I'm going to turn on another math function. This time let's use measurement trend and change it to a smoothing filter based on the max hold waveform, and let's smooth it based on 200 points. And now I'm going to zoom in on this waveform and 200 points doesn't roll off the bandwidth of this signal. Now I have a nice smooth signal for which I can measure the settling time. The settling time I would do just like I did the short beacon, measure from 0 to 90%. I'm going to skip that. Same thing with the slew rate. If I want to measure the slew rate, I'd set up again another math function, scale it by a factor of 0.707, make a rise time measurement from 45 to 55, and then turn on the cursor menu so I could read off the delta Y over delta X to get the slew rate. To measure the frequency and current RMS, let's go ahead and turn our math functions off, turn our measurements off. Just like I did with the short beacon, I could zoom in to 2 microseconds per division and again measure it just like I did for the short beacon. For our last measurement, and that is the overall cycle time of all the beacons, and that's called T long beacon period, we set up an entirely different trigger condition. So let's do that. I'm going to turn off zone trigger. I'm going to change my trigger condition. Pulse width is what I want, channel 1 low, but I'm going to change it to greater than 100 milliseconds, less than 160 milliseconds. And the next time it triggers, you're going to see that it should lock on to the first short beacon following a long beacon concatenated to a short beacon. The T long beacon period is the time between, you can see this concatenated short and this concatenated short. To measure that, I'll turn the math function back on. I'll start with my max hold waveform you've seen several times already. And now I'm going to turn on a second math function called measurement trend based on math 1 based on plus width measurements. And now we see a pulse every time a long beacon occurs. It's on this waveform that we can now measure that period. If I select measurements, select a period measurement on my math 2 waveform, we're measuring 3 seconds. The specification for the T long beacon period is 850 milliseconds to 3 seconds. So you can see I set up pretty much the worst case or long condition on my arbitrary waveform generator. Thanks for watching this short video. Remember, we have 2 other videos. The next one's going to be on power and efficiency measurements during the power transfer state. We also have 3 application notes that go along with this 3-part video that actually provides more details as well as step-by-step instructions. I encourage you to download them at the URL listed on your screen. And if you haven't seen the other 2 videos on these wireless charging measurements, I encourage you to watch those as well.